before we move beyond the tail bound, let's very quickly look at how well they actually work in practice, because it's quite instructive actually what's happening. So let's use it for something like hypothesis testing. And well, the simple question is, I have two web page layouts and I want to find out which one's better. And I could, of course, use my designer, and the designer will say, yeah, this is good. Or I could actually say, well, let's use the scientific method. We test and we see how it works. So one nice randomized experiment is, well, half of the users see design A, half of the users see design B, and then we check how much money I'm making, or how many clicks I get. So this is slightly more ethical than doing the same thing with drugs. And you get the results a lot faster and nobody will complain. So let's just, for the sake of the argument, assume that, P of A, so for design A, the probability is that 10% that somebody clicks. In other case, it's 11%. So they're fairly close. Let's see how much we actually need. So let's start. So Gauss-Markov doesn't really help us in this case, but the Chebyshev inequality might already give us something. So we need to bound for a deviation of 1%, and well, we know that the true mean is actually 11%. Well, we actually don't really know this yet, but we want to, actually make sure that with only 5% probability, we don't pick B. Okay, so we have absolutely no prior knowledge about how good the system is. We can, of course, bound the variance. Y sigma squared is, 0.25, right? So that's fine. And then, we plug that in, and we get that we need about 50,000 experiments until I can tell with sufficiently high confidence which of the two designs is better. Okay. Now, if we actually know that the click probability is at most maybe 15%, well, then we can bound the variance accordingly. Sorry, that may have actually been wrong here. No, that's its sorry. Yeah, and we get this for the variance. When we plug it in, we get about 25,000 users. So by having a little bit more prior knowledge, I need half the number of users. This is a big deal, because that actually means money. It basically means, first of all, I can tell 25,000 users earlier which design is better, and I will also then be making more money off those additional 25,000 users.
How would you know that number?
Well, that's exactly what we get from this bound, right?
No, I mean, how would you know the upper bound and the probability?
So maybe you can reasonably well assume that your users are not going to go into a buying frenzy. The other thing is, you can actually also assume that the only thing you're really worried about is that plan B is worse than plan A. So you could even bound it conservative by 0.1. Because it's not a bad problem that you have if your variance is larger. So in that sense, you're actually being conservative anyway to pick like 0.15. Now let's do something slightly tighter. So Hoeffding's bound gives you slightly better estimates. So we know it's a random variable that has bounded range, click or no click. So C equals 1, and then we just solve Hoeffding's inequality, so we plug in all the numbers, and voila, we get about 18,000. So it's better than what we had before. Before we had 25,000. The problem is that it's actually fairly pessimistic, because Hoeffding is actually really good at probabilities around 1/2, and it's not so good at probabilities close to 0 and close to 1. The KL divergence, for instance, if you were to plug that in, would give you better guarantees. Now, what can we do even better than that? Well, I could basically throw all the caution to the wind and make a normal approximation. Now, this is an approximation, it's not a bound anymore. But it may be good enough. So I'm just, explaining the fact that I'll have asymptotic normality, and then I look at, the Gaussian interval containing, 0.95 probability, right? And in order to get this, well, I can work out that epsilon is given by 2.96 times sigma. So you can actually read it off the table. In this case, well, again, let's take the same variance bound as what we had before. I plug that in, and voila, I'm down at 11,000 instances. Now that is a little bit risky because, of course, it's not quite true that the central limit theorem kicks in because we are not truly in the asymptotic regime, but we are close enough. And I've had a couple of experiences where statistical tests that we designed, the asymptotic analysis beat the finite sample size results at sample sizes of 10 or 20. They were more accurate. So bear in mind that this is an approximation, not a bound. But if you actually care about dollars, you may very well want to go with the approximation. Now, well, of course, just checking whether people like a blue or a black page is boring. You might have actually a lot of different layouts. You might have some combinatorial strategy. Let's say you can put 2 different modules on the left-hand side of your web page. You have 5 different ways how you display the main content. You get to choose where you put the ad, maybe on top, the bottom, left, right. You can choose what you put on the right-hand side. So you very quickly get the combinatorial explosion of different things that you can put on a page. They might also start interacting with each other and so on. So at this point, the simple hypothesis testing that I showed you isn't going to cut it anymore. And then you need to do quite a bit more modeling of how the user might actually interact with the page. And you will need also slightly fancy algorithms to determine which attribute combinations you should try out, because you might not even be able to try out all combinations. This will get us into active learning, and we're going to look into that at the very end of this class. So probably sometime in April. And yeah, this is just a heads up for the really fun stuff that you can do with more or less the same techniques. So here we had basically a binary decision, red or blue. There we will have a very large parameter vector that we want to tune. And in some cases you can still get decent regret guarantees out of the algorithms, and it leads to very interesting scenarios. Question yet?
You mean the Chinese restaurant process?
No, this is a made-up name, the Thai restaurant process. I call it this way because, okay, so I hope no Thai will be offended, but whenever you go to a Thai restaurant, it's amazing how many different dishes they have on the menu. And it's usually you can get red or green curry or Penang curry or jungle curry with chicken, beef, vegetarian or tofu, with different types of rice, with different types of side dishes. So quite often you can actually factorize the menu of a Thai restaurant into a small number of ingredients that are then combined on the spot. That probably applies to other countries' dishes as well, and I'm probably being very unkind to Thai here, so I hope nobody is really offended. But okay, basically go to restaurants with a very large number of dishes and you will be able to factor them very nicely. And not always all combinations will be served. Yeah. So that's just why I flippantly called it the Thai restaurant process of combining things. Okay. Any other questions? And yes, by the way, we will probably do the Chinese restaurant process later on, but that'll take a while. Okay, kernel density estimation. So one of the key guys here is Emmanuel Parzen. And this is actually going to be fairly straightforward. So who has done kernel density estimation before? Okay, about maybe 1/3 of the people. So let's start with something very simple here. So we take discrete bins. So let's say male, female, English, yada, yada, yada. And we can just apply the union bound and then Höfting. So in other words, the probability that the super will, the deviation between empirical average and true probability is larger than epsilon. I can just bound that by, in this case, actually, 2 times set of size of that set times e to the minus 2m epsilon squared. So the factor of 2 comes from the fact that we want to get upper and lower bounds. Then I can just solve for the error probability, and life's good, right? The log of that domain and the log of the error probability, so both things don't actually hurt me that much. So as long as my set of alternatives isn't too big, well, I'm fine. So why bother? Well, here's an example. Well, let's just sample from some underlying density. And I could just, put the discrete distribution there. And that's, of course, horribly bad, right? And you can immediately see what's going wrong. Let's, just take, 10 bins, maybe in the interval between 0 and 1. And then, I have maybe 10 dimensions. Then, I get 10 to the 10. And, well, that's a ridiculously large number of bins. So the data structure holding all that data would already be an interesting object. Now, what's even worse is that the probability mass per cell will, worst case, also go like, 1 over 10 to the 10. So in other words, most bins will be empty, and the ones that have something in it won't have really much things in it either. So, well, on the other hand, in one dimension, actually, bin counting is not so horrible, right? This is bin counting. And it works reasonably well. Now, the naive idea in Parzen Windows is, well, if we could smooth this out a little bit, we'd be in business. And that's what Parzen Windows really does. We take the empirical distribution, this guy here, and we smooth it out with some kernel function. So this is a smoothing kernel. It's not a Hilbert-Schmidt kernel. So it's not a kernel as in kernel machines, but a kernel as in kernel density estimation. Yeah.
Do you start by saying what a kernel is?
Okay. I will show you that, and the equation is down here. So the smoothing kernel has the property that if I integrate out of its argument, it integrates out to 1, and it should be centered at x, and, well, it's non-negative. That's pretty much all you require. There are a couple of those kernels which are better than others, and you'll see some of them here. And so this is, it's basically, you're approximating everything by, a lot of Gaussian bumps that you're putting where the data is. You can use Laplaces. You can use this thing called the Eponichkov kernel, which has finite support. It's basically a parabola that's been chopped off. Or you could just take indicator functions. Even those are not too bad. Now this one's quite popular because it has, finite support. So therefore, any data that's, sufficiently far away from the point around which you're expanding isn't going to hurt you. So, given the interests of already in kernels as in kernel machine kernels, let me quickly show you what the condition is that they need to satisfy. So one condition that they need to set, so this is the condition for Mercer's theorem, so K is a function of two arguments x and x prime. So don't worry, you won't really need that for anything in this lecture, but just to explain that point. And it needs to satisfy the condition that for any f, the integral f of x prime, k of x prime, dx prime is greater or equal than 0 for all f. And there are various conditions that you can impose on, the measure on the space and so on. But essentially, so this is the operator version of requiring that v transpose mv is greater or equal than 0 for all v, which you've probably seen before. It's basically a matrix with no negative eigenvalues. And this essentially is the integral version of simple vector transpose the matrix vector. And there are corresponding expansions in terms of the eigenfunctions, eigenvalues. We'll do that later. But this is the kernel in terms of kernel machines kernel. Now, it actually so happens that some of these beasts here satisfy these conditions. And that's what causes an awful lot of confusion. Also not to be confused with operating systems kernels. You would think, who would do that? I remember many years ago I got an email from somebody who was very proudly contributing to the Linux kernel, who wanted to do his PhD with me, because he had experience with kernels. No, he didn't. No, but actually I got that email, and I told the guy gently that this was a very different beast. So, what really matters is the size of the kernel. So if I pick smoothing kernels of different widths, I will in some cases get complete utter garbage, like here. Or here where it over-smoothes probably rather much. And here this is probably closer to reality. Actually, it's probably somewhere in between here. Now, how do we actually get that kernel width right? So let me first show you how you actually adjust the kernel width. What I do is I basically take some function h, which is that Parzen Windows type of kernel. I take x minus xi, centered at xi, and we scale by r. And then I need to multiply it by r to the minus d to ensure that it integrates up to 1. Question, yeah?
Do all kernels that we're using for kernel density estimates decompose in this way?
They don't have to, but it turns out to be computationally very convenient. So in some cases you may have different r's for different locations, and I'll show you that in a few slides down the track. They don't have to do that, but most of the things that people implement do, sometimes just for computational convenience. If you have a specific idea that in certain parts of your space you should be using different kernels, then you should absolutely go for it. The other thing is, if I have a discrete domain, let's say text, then this is complete utter garbage. I cannot rescale words, right? I can't have 3/4 of a word occurring. But for, Rn, this is not a bad thing. Now, here's the problem. If we pick a kernel that's really, really narrow, it's going to overfit. And with overfit, I mean that the probability p of xi is actually going to go to infinity. Because what will happen is that this kernel will just peak more and more around the point around which I'm expanding it. So you can already see this happening here, right? So therefore, if I just perform maximum likelihood fit, when I look at the likelihood of the data under the choice of this kernel width, I will have r going to 0. This is obviously nonsense. Right? The other problem is if I then just play it safe and pick a really large r, it's going to underfit. It's going to oversmooth completely. So how do we actually choose it? There's a whole bunch of tools that you can use. One of them would be I use proper statistical analysis and look at rates of convergence and do a fair amount of work to get good rates. And there are very impressive papers that people have written about this, about specific kernels. Okay. Are we going to do that? No, we're going to be lazy. We're going to do something ridiculously simple that also does the trick and doesn't require a lot of skills. And it will probably actually beat the other methods. So, okay, so to give you a bit more of an idea, so here's some data that we've drawn, we've smoothed, and if we smooth with different kernel width, okay, we need to do capacity control. So we need to make sure we don't overfit, and one idea is to have a validation set. So we just pick some data and we set it aside for calibrating the scale. We probably won't need a ridiculously large amount of data because it's just a single parameter. So there's not a lot of model complexity that we might run into here. I mean, yes, okay, VC dimension is not identical to the number of parameters, but number of parameters is a pretty good, back of the envelope estimate for how complicated your problem is. So we go and set that data set aside, and we could just, maybe pick 10% of our data set, set it aside. We compute our density estimate for the remaining 90%, and we check how well the likelihood is behaved for the remaining 10%. But that's sort of wasteful because we're basically not using the remainder of the data to actually estimate our parameter. On top of that, it's actually computationally not so convenient. So let me just show you a little bit what happens. Okay. So log of p hat of x prime, so this is our validation set, okay, which is the sum of those logs. Now, this is basically summing over all x prime, log of, here's the sum over all x in the data set that I'm using, here are the kernels, and then, I just get the usual rescaling here. That's just, sample size division and so on. So that's basically, that's not a big deal. But the scale here already shows up. So, that scale you could see showed up because we had it as a scaling factor up front, all of those kernels. So taking the log separates it out. That's what it gets. Now, for leave one out cross validation, it's actually even simpler because, so basically the idea is we take all the data but a single instance. We compute a density estimate using all the data but that instance. And we then look at the likelihood for that instance. And we average that log likelihood for all the other instances, for the entire data set. So this is essentially a flavor of a leave one out estimate. So here we divide by all the x's logged in that data set. We need to rescale correspondingly. But the good thing is I can rewrite that in terms of the full expression, and I just subtract the kernel at position 0 if I have a kernel which depends on x minus x prime. So I'm basically only subtracting a constant from that and rescaling. So taking the sum over the logs of these terms, it's just this upfront constant which doesn't really factor in. And then here we have the log of p hat of x minus m inverse r to the minus d k of naught. And I can go and plot that curve. And so, it'll peak somewhere. It's reasonably well behaved. And I pick the peak and say this is probably going to be a good estimate. And it gives us something that's not horribly wrong. Yep?
The x-axis is r.
The x-axis is r. Yes, you're absolutely right. Well, not on this plot, but on that plot it was. So kernel width, that's what we have. This is for one dimension. And as you could see, I plotted it in log of that scale, because what you really care about is getting the scale right, rather than getting the actual number right. There are nice arguments, for instance, for consistency of nearest neighbors and so on. There's a beautiful paper that was proven by Sami Tufe. I'm not sure, I've probably butchered his last name completely, at NIPS this year. And apparently those two letters you don't really pronounce, and it's, yeah. He told me it means that some jaguar is angry, but yeah. At least it will help you find the paper, and if you like that kind of analysis, it's actually very nice. Okay, now, here's a problem with our density estimate. So, it's kind of a chicken and egg problem. So, in a way, we want to have a wide kernel where we have very low density, because our density is not going to be uniform. If it's uniform, then I don't need a kernel density estimation in the first place, right? And I just say, well, density is constant. So we want to have a wide kernel for low density regions, because there we will have very little data to make sure we smooth suitably. We want a narrow kernel where we have a lot of data. Suppose you want to do a population density estimate of the United States, then somewhere in the Midwest, there's a lot of land where there are hardly any people, and then you get cities like New York, San Francisco, whatever, where you have they have very high population density, but it's still non-uniform throughout the city. So you want to have a very narrow scale in the cities and a very wide scale in the countryside. So, of course, if we knew the density, we could automatically adjust the density scale, but that's, it's a chicken and egg problem. So, doing density estimations to get the density is kind of, to get the parameters for the density estimate is kind of stupid. So, Silverman's trick was actually quite ingenious. So he basically said, well, you know, let's look at the k-nearest neighbors of an instance, take the average distance, and, you know, scale it by some fudge factor. It's like maybe 1/2 or so, and use that for a locally and therefore non-uniform density scale of the data. And, you know, there we have the true density, and the non-adaptive estimate is, well, very non-adaptive, as you can see. And the adaptive one gets things right both in the high and low density regions. And if you look at it, this is a bit of an idea of the distance distribution that you get, and you can see that there's clearly a fair number of instances that are very close, and there are some that are very far from each other. Okay, so how can we use this? This is actually going to give you the, you know, a very, very simple but very well performing classifier in regression estimator. So this is the Watson-Adaria estimator. So nice things can be proven about them, but we're not going to bother in this class here. So it's just because there's not enough time. So given pairs x and y, we would like to estimate y for a new x. So what we could do is we could just, you know, use the distance weighted average of those y's and come up with this estimate. So y hat of x is then, you know, sum over yi, k of xi of x, divided by, you know, the overall density here. And these are basically weighting coefficients. So this is locally weighted, and, you know, those xi's that are close to x are going to gain a high weight, and those that are far away are going to get weight close to 0. So this is like a local weighted average of labels. So it's much more sophisticated than a k-nearest neighbors, because k-nearest neighbors just takes the k-nearest neighbors and throws away everything else. So k-nearest neighbors just picks the nearest neighbors and does a majority vote. This does a weighted nearest neighbor like average, and it also makes sure that all those weighting coefficients always nicely sum up to 1, and that your scale automatically gets wider as you get to low density regions. So, divide it back so. I'm just going to derive that in a slightly different way. So the argument goes as follows. Let's say we have, you know, class 1 and class -1, and each of those creates some instances. So class 1 maybe creates instances x1 up to xn, and class -1 is going to create instances x1 prime up to x prime n prime. Okay. So in that case, I can come up with, you know, Parzen Windows density estimates for classes 1 and -1. So I get, you know, p of x conditioned on y equals 1 is just, you know, the sum 1 over n sum over I k of xi and x, I equals 1. And we get the same thing for p of x given y equals to -1. Now if I'm interested in getting p of y given x, right? Now I can work that out, right? So times, so this equals p of x given y divided by, in this case I need to, I get p of times p of y, and then divided by p of x. So that's, in this case, p of x given 1 and p of 1 plus p of x given -1 and p of -1. So far so good. So there's really nothing special going on here. Now let's expand those terms. This expression here can be written as just a standard kernel density estimate for the entire set. So this is going to be 1 over n plus n prime, sum over I going from 1 to n plus n prime, k of, you know, xi or prime or whatever, a prime here, a prime here, and x. So that's the denominator in this expansion here. Now, suppose we actually want to classify whether this is class 1 or minus 1, depending on, you know, whether it's above 1/2 or below 1/2. Then I could equally well take p of y equals 1 given x minus p of y equals minus 1 given x and look at its sign. Right? So I can basically write here, so minus this, minus 1 given x, minus p of, you know, x given minus 1 times p of minus 1. Now, this can be written exactly as the numerator. And we have the Parzen Windows classifier. That's how you can derive it. Any questions so far? Okay. So it's very, very simple. Let's see what it does. So here's it is a data set, and here's the Watson area classifier. And you can see reasonably nicely that it produces something, you know, that's, you know, quite close to a German flag. So, and it probably classifies something here. Okay, so this is, you know, with maybe 3-4 lines of code, and then maybe, you know, one function evaluation for that kernel function, you can get a nice non-parametric classifier. It might be very slow, so you might not necessarily want to, you know, build your big startup around it, but it's a very quick and dirty way of actually checking whether this is not too stupid. Now, the ingenious insight of what's known in that area was that, you know, there's no reason why those yi's need to be only 1 or minus 1. You can just make them any scalar that you want. And if I do this, I get a regressor. So it's the true function, here's the regression estimate, and if you're not sure how well you can see green in the back row, but you can see it's not too horrible. Okay, so this is a simple regressor. So k-nearest neighbors, as already mentioned, well, it just simplifies things rather much more. You just give everybody the same weight. You have the same number of neighbors throughout. And then for classification, you just use the majority rule, and for regression, you can just average the layers. Okay. And for that, it's not so hard to prove consistency. So one way of proving consistency in this case, for instance, is to look at the size of those, you know, k-nearest neighbor sets. And you want to, as you get more instances, of course, the size of those sets is going to shrink. And so what you do is the size shrinks, you let the number of instances for that set increase slightly, and then you'll basically see that, unless you have something very pathological, you know, point-wise, that this, you know, the conditional probability estimates are going to converge to, you know, their limit at that point. And yeah, that's more or less how you can hack a convergence proof for k-nearest neighbors together. Any questions up to this point? Okay, everything clear. Good, then, well, we can do exponential families, and we might even get through with them. Who has done exponential families before? Okay, cool. So everybody knows this stuff, right? Good. So we're going to have a lot of fun with this now. So the first thing that we'll do is we'll actually try to figure out, how on earth did we end up with this expression, right? So, okay, let's for the moment assume I'm interested in, having some density estimate, which is parameterized by some function, which by the exponential of some function. Now, and that is going to be something possibly non-parametric later on. Now, in order to ensure that this is all well normalized, we need to have this g of theta, which ensures that things sum up. And the condition is clearly that g of theta is just the log of, if we have a discrete domain, sum over all the x primes, e to the phi of x prime dot theta. Okay. Now, if we have a continuous domain, and so basically the thing that I didn't really specify is that we might have different measures. So for instance, for the Poisson distribution, we have a counting measure and we have the 1 over x factorial as the actual measure, but unless specified otherwise, we'll either have the counting measure uniform or we'll have the living measure. So just throwing a lot of mathematical details under the rug here. Question, yes?
By bracket, by x theta, we mean?
That's an inner product. And I'm going to show you with a little bit more details what this actually means. So don't worry, we'll get to the normal distribution and Poisson and so on and actually go through this. So one of the reasons why people really like this is the fact that the derivatives of this function g gives you a lot of information. For instance, the first derivative actually gives you the expectation of phi of x. So these things are sometimes called the sufficient statistics of that distribution. The second derivative gives you the variance of this. And so there's actually a nice paper by Peter Orbans who shows that this is actually a nice universal approach if I pick the right set of functions. Let me write up that name. He might have a team here, I'm not quite sure, but in any case, he's in Cambridge. Okay, so who knows why this holds? Okay, let's do the derivation. It's the kind of derivation you want to do once, and then probably not again, but okay. So, d theta of g of theta. That's d theta, the log of the sum over all x e to the phi of x with theta. Okay? Which is the same thing as 1 over sum over x e to the phi of x with theta. Now here in the numerator we have sum over all x phi of x times e to the phi of x with theta. Right? Nothing special has happened here. We've just taken derivatives mathematically to do that for you. Now, the cool thing is that this, of course, is nothing else than e to the g of theta. Right? Now, since this is e to the g of theta and I have an exponential here, I can plug it in there. So this guy comes in here. At which point we have e to the phi of x dot theta minus g of theta. But we know that quantity. That's exactly our p of x. Okay? So I can write it as the sum over x, phi of x, p of x, parameterized by theta. And everybody recognizes that quantity, that's exactly the expectation. Okay, good. So, that's the slide here. People use it in both directions. If you have theta and g, then things are fairly easy and you can just, work out algebraically what the expectation has to be. This is sometimes much easier than actually solving other integrals. And by the way, the same thing holds for the variance. Furthermore, if you don't have g, in some cases you can compute an estimate of that expectation. And that's what you may need in message passing algorithms when you run loopy belief propagation or something like that, to come up with a good idea of what the expected gradient is going to be, and then you take update steps. So this is probably one of the most important equalities in that context. Now, can somebody tell me based on this why G has to be convex? You've answered too many questions. Yeah.
The second derivative is greater than or equal to 0.
Correct. Because it's a variance, and the variance has all eigenvalues greater or equal than 0, so we're safe. So this is very nice because it means that actually maximum likelihood estimation problems where we want to maximize this quantity here. So this object here is log concave in theta. And so therefore, if I minimize the negative log likelihood, I get a convex optimization problem. And a lot of beautiful things happen if I have convex problems. So let's look at a few examples. So we've already seen this one, right? Binomial distribution, phi of x is x. And so x takes on values 0 or 1. And this allows me to, come up with a distribution with two different numbers. Let's add up to 1. I could have a discrete distribution, and then I just take Ex to be the unit vector. Let's say, for instance, if I have people from 5 different countries, I pick Ex to be the unit vector in R5, and it's just going to pick out the corresponding coefficient vector. Now that still looks awfully much like just algebraic manipulation, and it is. So those of you who have probably worked at some point with the softmax function in neural networks, that is basically the thing that you're going to do. Now something slightly more interesting, a Gaussian. In this case, phi of x is x and 1/2 xx transpose. I'm going to derive that for you. And the entire trick is just to take a Gaussian and make a big mess of it. So, d of x, parameterized by mean mu and covariance sigma, is going to be 1 over 2 pi to the d over 2, determinant of sigma. And then here we have e to the minus 1/2 x minus mu transpose sigma x minus mu. Sigma inverse here. Okay. Now, I'm going to turn this all into an exponential. So the first step is, and the other thing I'm going to do is I'm going to peel out all the terms in x, in xx transpose. So this equals exponential of some big piece. So we have minus d over 2 log 2 pi. We have minus log determinant sigma. We get minus 1/2 x transpose And here we have a trace between this times sigma inverse. So that just happened by taking x transpose sigma inverse x, moving x to the left hand side, and then I get a trace. There's nothing else happening. Then I get plus, well, mu transpose sigma inverse x, and then I get a minus 1/2 mu transpose sigma inverse mu. Okay. Now this is basically all we need. Because we have our sufficient statistics, minus 1/2 xx transpose and x. That's exactly our phi of x. And then you can go and express the entire rest here in terms of these new parameters, which I'm just going to call maybe theta2 and theta1. And it's a bit tedious, but you'll then get an expression in terms of these new parameters, which is convex in them. Whereas before, the problem was not log convex, log concave in mean and covariance. So all of a sudden, you can actually estimate mean and covariance through a convex optimization procedure. Well, why would you care? If you, for instance, have a heteroscedastic estimation problem, you can now turn it into a convex problem. It's very straightforward. So, given that we're a little bit short on time, I'll leave the last 5 minutes for any questions that we have. And given that we went a bit over time last time anyway, so I don't want to overdo it this time again. So we'll wrap up the rest of the exponential family next week, and then we'll get to data stream algorithms. Question? Yes?
Sorry, just real quick, could you flip back to the definition slide? For
Yes,
notation?
absolutely.
Thanks.
And again, those slides will be online sometime tonight. And the lectures will be up online probably sometime tomorrow, as soon as I can upload maybe half a dozen gigabytes. So as said, it's very much in your interest to team up for projects and to do it soon. Because otherwise